The second thing is, now assume that you have a loss distribution and you want to put a number on this loss distribution. You want to measure your risk. And this at the end always means coming up with a number. Now, why would you want to do this? Where does this issue arise? A risk measure, as I just said, is a mapping which sort of associates a risk, a loss, with a number. This issue arises in all amounts of capital calculations, be it economic capital or regulatory capital, because capital, the amount of capital you need is always going to be a number. And you're asking yourselves, how much capital do I need, or how much of this position do I need to finance with equity so that the risk is acceptable either for an external regulator or for the risk appetite of the company internally. You can also use risk measures as a limiting tool. So suppose you have a bank or maybe also an insurance company, and of course you have ambitious traders there and they think they know the market very well, and you think that also because otherwise you wouldn't have hired them, but still you want to limit their activity a little bit. And one way of doing that is by saying, okay, you may trade German equities as you please, but please make sure that the value at risk of your portfolio is smaller than 10 million or something. So as a limiting tool, risk measures are being used. And of course, in a sense, pricing of insurance, also finance, also requires you to put a number on risk. Approaches to risk measurement, let's go through this very, very briefly. So the idea of this slide is to go one step back, like that, and to see what types of risk measures are there, how can we classify them. One idea is sort of the notional amount approach. You say the risk of a portfolio is essentially equal to the size of the portfolio, to the sum notional values of the securities. Then we may say this is stupid. There are good reasons why, but it's still being used. Standardized approach of Basel II still does something like that, and there's also in the current debate, regulatory debate, are ideas that you should also look at the notion or the size of the balance sheet, which is basically the same thing. The problem is, of course, that you completely ignore such things as netting or diversification when you do that. Most risk measures which we find, we already mentioned value at risk or others, are in fact statistics of a loss distribution. So you look at the loss distribution and then have a distribution and try to measure the risk inherent in a loss distribution. Variance or volatility is maybe the oldest risk measure there. Value at risk and expected shortfall are very important. The nice thing about this approach is that it makes sense on all levels, so you can do this both for a single position or even for the P&L of an overall financial institution. It does reflect netting and diversification, of course. If you have two positions that cancel each other out, your loss distributions will have a smaller variance. A third approach, which is also in use, are scenario-based risk measures, and we will see later that this third approach and the second approach, even if they seem to be completely different now, are in fact somewhat linked by a general theory. Scenario-based risk approach, there you come from stress testing, say maybe as the stress test for the European banks, which happened a couple of weeks ago. So, but to really, or you find this idea also very much when it comes to computing margin requirement for trading at exchanges. Wrong one. You consider potential future risk factor changes or scenarios, for instance, a 20% drop in a market index or a certain interest rate environment or something like that. And then you say that the risk of the portfolio is the maximum loss under all scenarios. And maybe you also weigh down certain of these scenarios. The idea of weighing down is, say, this is a very hypothetical, very extreme scenario, and I don't want to take it into account 100%. but I still want to see what happens to the portfolio of this bank or insurance company under that scenario. Good. So how can we write this down given the formalism we have introduced so far? x1 up to xn are the risk factor changes or scenarios we might consider: the drop in interest rates, a drop in GDP, whatever, the hurricane or earthquake in Tokyo, or this type of scenarios. And each of these ones is given a weight which could be considered as a measure of its plausibility. The weights are between 0 and 1. And the risk measure is then the maximum overall scenario of the loss. L of xi measures the loss given that this scenario occurs, and we may weigh it down and we take the max of all these numbers. As an example where this really happens, you find it in detail in the book, is the standard portfolio analysis of risk, which is being applied at the Chicago Mercantile Exchange. There the scenarios are easy to define. You are trading futures on certain indices, and so you have up and down movements, and if it's also derivatives, so also up and down movements of volatility and certain combinations of those. It's a narrow set of, I think, 14 scenarios. Good.
That's also what the standard formula of Solvency II does.
This does also such things, yeah. X is a scenario and you assign it a certain probability, sort of. The idea is if you, it does make a difference, okay. It does make a difference if you compute the loss, say, take banking, the loss of your portfolio given that interest rates rise by 5%, and you say that's very unlikely, that's why, then you make a certain, well, you have a profit or loss. Say you make a loss, and you have a loss of 100 million, and then you say this was a very extreme assumption, so in computing this maximum, I weigh down the loss. If you would move the W inside, say the W is 1/3, then you would not consider an interest rate change of 5%, but only of 5/3, so 1.7%. The xi itself is a vector of changes, and you assign it a certain probability, which is the W. Now, each of the W is between 0 and 1, and so 1 minus W is the probability that it does not happen. W is the probability sort of that this risk factor change happens, and 1 minus W is that it doesn't happen. They don't sum up to 1 directly. Good. So mathematical interpretation of this. Good. So L of 0 is 0, so if nothing happens, your portfolio value doesn't change. If delta t is small, that's fine. Then you say, as I just mentioned, W L of xi, you can write this as Wi L of xi plus 1 minus W times L of 0. And you can view this as the expected value of L of x when you say the probability that this risk factor change happens is maybe 1/3, and the probability that it doesn't happen is 0.7. This is not the true probability, it's something which you artificially assign. And then you can write this weighted risk measure, which we've seen here, this max here, as slightly more abstractly, as the maximum of the expected value of the loss under certain probability distributions, namely these here, where you say Pi is that with probability Wi, we see the change delta xi, and with probability 1 minus W, you see nothing. Now you may ask yourself, why on earth do I have, okay, I understood the simple formula, but why do I have to write it so complicatedly? The answer is that this complicated way of writing it is a way in which you can sort of write every risk measure which belongs to a certain class, namely the so-called coherent risk measures. And this weighting down of certain scenarios is also something that happens in real applications like this bond portfolio. Good advantages. It's a completely different setup first. Of course, it's particularly useful, of course, for making margin requirements. There you have to be able to compute quickly, and you can define the scenarios easy. It's a different thinking. You ask yourself really more, what happens to my portfolio if this and that happens, which is, of course, very useful complementary information. So that's the advantage of this type of approaches. The challenge, I wouldn't say it's a disadvantage or a drawback, but the difficult thing is, of course, what are the right scenarios to consider, and this can lead to endless arguing. And for instance, in this European stress test, banks said, well, we know that we were not particularly good at this stress test, but we think the scenarios the regulator picked are not really representative for the dangers we are facing, and you can argue all the time about that. Good. Now let's look at a very specific risk measure, value at risk, which is very popular in banking and insurance, and which is a risk measure based on the loss distribution. So for loss L, the value at risk at the confidence level alpha in 0 and 1 is the smallest number such that the probability that the loss, smallest number x, such that the probability that the loss is smaller than x is bigger than alpha, or the probability that the loss is smaller than x is smaller than 1 minus alpha. So in statistical terminology, it's just the alpha quantile of the loss distribution. Most of you know it. Probably for those who've seen it sort of for the first time, it may be useful to look at the following picture. If this is the distribution function of our loss here, then to compute the value at risk at a confidence level of 95%, you have to look for that threshold such that the probability that the loss is bigger than the threshold is 5%, or the probability that you're smaller than the threshold, so that's the white thing here, is equal to 95%. And if you move your confidence level further up, so if you go to 99%, say, then you need to have 1% mass to the right or 99% to the left. The idea where it was first done is in 1994 in the Weatherstone 415 report. I should explain maybe the terminology because this was already old when I was young. The idea is Weatherstone was the chairman of JP Morgan in those days, and he wanted to understand better. It was the time when derivatives were really coming up, the risk he had in his trading book, and he wanted by 4:15, so a little bit after the market closes and before he went home or to the golf court, he wanted to have a report on the riskiness of his portfolio, and ideally a number. And he wanted it by 4:15 in the afternoon. That's my 4:15 report. And to meet this challenge, this risk metric group developed this idea of linear normal distribution based modeling, and then they had a normal distribution describing the P&L of the portfolio, and to summarize this into one number, which they could present to the CEO, they came up with the concept of value at risk. Now, what is the most important sort of drawback of value at risk immediately without going into a deeper theory? Well, it's not a what-if measure. It tells you, okay, the value at risk of your portfolio, say the value at risk of JP Morgan over one day is, let's take a number, $50 million. This means that with the probability, say at 95% level, with the probability of 95%, they will not lose more than $50 million. Well, that's nice. But what happens with a probability of 5%? What happens if you go beyond that threshold? Is it then most likely that you will lose maybe $55 million, or are you then do you then have some very exotic products in your trading portfolio that can create losses only very rarely, but if then they hit really big, maybe some weird securitization deals or something, and then you're ending up with whatever 100 or 200 million losses very quickly. And value at risk, at least if you fix one confidence level, one alpha, doesn't answer that, which is of course a problem with this measure. example, so that's just very quickly, there we compute the value at risk for normal and the t-distribution in this example. If x is normally distributed, then you can immediately, and this is not specific to the normal distribution, it's clear from the definition of value at risk as a quantile that if you scale and center a distribution, then the quantiles are also being scaled and centered. So the value at risk is just, if you take a normal distribution with mean mu here and variance sigma squared, of course, if you subtract mu divided by sigma, you get a standard normal distribution, and the quantile is just the mean plus the standard deviation times the alpha quantile of the standard normal distribution. And this is not specific to the normal. This holds true for every distribution. So you can sort of move centering and scaling outside computing quantiles. And so it's given by you have to need the mu, you need the sigma, and then the alpha quantile of the normal distribution. The same thing also works for the t-distribution. The t-distribution is also a symmetric distribution. Many properties are similar to the normal, but it does have more mass in the tails. And the value at risk also has this property here.